Welcome to the Neuroplasticity tutorial. Synaptic plasticity signifies the phenomenon of changes of synaptic strength among neurons. These connections can be strengthened or weakened over time in response to activity. There are two different types of synapse connections, which are excitatory and inhibitory. Excitatory synapses increase the likelihood that the postsynaptic neuron will fire an action potential by depolarizing the neuron, making it more positively charged. Inhibitory synapses decrease the likelihood that the postsynaptic neuron will fire an action potential by hyperpolarizing the neuron, making it more negatively charged. Viggi has support for both excitatory and inhibitory synapses. Plasticity is a fundamental mechanism underlying learning and memory. Neuroplasticity can be categorized into multiple types such as Hebbian plasticity, homeostatic plasticity, metaplasticity, synaptic scaling, structural plasticity, and long-term potentiation or depression. Viggi currently supports the LTP and LTD mechanism built on the STDP or spike time dependent plasticity principles. Long-term potentiation is a persistent strengthening of synapses between neurons, resulting in enhanced communication between them. It occurs when repeated stimulation of a synapse leads to increased efficiency in signal transmission. This process involves changing the structure of function in synapses, such as the increase in neurotransmitter release or the number of receptors of the postsynaptic neuron. For example, if you're learning how to play a new song on the piano, initially your brain forms weak connections between the neurons involved in finger movements and those responsible for auditory processing. As you practice the song repeatedly, these connections become stronger, making it easier for you to play the song flawlessly in the future. Long-term depression is the opposite of long-term potentiation. It involves a persistent weakening of synapses between neurons, leading to reduced communication efficiency. LTD occurs when synapses are repeatedly activated at low frequencies or when there is a decrease in neurotransmitter release or receptor density on the postsynaptic neuron. For example, when you've been practicing a skill, like riding a bike, if you stop practicing for an extended period, over time, the connections between the neurons responsible for coordinating balance and motor control may weaken due to a lack of stimulation. As a result, when you attempt to ride the bicycle again after a long break, you may find it challenging to maintain balance. For context, synaptic plasticity is the process of neuroplasticity occurring at the synaptic level. Neuroplasticity can be considered as a superset of synaptic plasticity and is the brain's capacity to reorganize its structure, function, and connections, which allow the brain to learn, adapt, and store memories. The intricate interplay between genetic programming, environmental influences, and activity-dependent changes highlights the brain's remarkable capacity for organization and reorganization through its life. Neuroplasticity underlies our ability to acquire new skills, adapt to new environments, recover from brain injuries, and compensate for neurological deficits, but disruptions in network formation and maintenance are linked to various neurological and psychiatric disorders. Viggi supports processes associated with developmental wiring, synaptogenesis, synaptic pruning, and synaptic plasticity, which will enable robots to better adapt to their environment and experience lifelong learning.